So today in this lecture, in lecture 4 of this course, we will go into the details now of the concept of optical diffraction. And so just to give you a few of the key words that we want to treat in this course, in this lecture, I will go to the visualizer now. So if you could just please put that on for me. So we will see how addition of coherent waves leads to interference. We've started on that in the last lecture and see that this is essential when we deal with optical diffraction. It's waves emanating from different points coming together at a point in space. We have to add up the amplitudes and phases of all those waves, and that will give us the pattern that is then limited by diffraction. So the concepts that we'll talk about is that imaging through finite apertures causes optical diffraction. The very important principle we'll try and discuss today is Huygens principle. Namely, that image patterns that we record in the microscope, or indeed any imaging system, arise from the superposition of spherical waves. You remember Huygens, Fresnel, in the first lecture I introduced this, where we saw how he imagined from this flame picture how spherical waves add up in space to give us the intensity or the amplitude at a particular point in space. So the most important, in fact the only important type of diffraction that we will talk about in microscopy, and again this is true for any imaging system, is Fraunhofer diffraction. So this is a particular type of diffraction where certain conditions are met, and we'll discuss what these conditions are. And these conditions are always met in a microscopy system. And so we need to understand how Fraunhofer diffraction arises and how to describe it, and then we can describe the image patterns that we see in a microscope. So, and finally, we will go through 2 examples to see how we calculate the patterns, the Fraunhofer patterns. The first one is diffracting light through a rectangular aperture, a slit if you so want, and you'll find that this yields a so-called sinc function. And then for the microscope, the most important one is what happens if you image through circular apertures, because lenses and components inside a microscope, they are round. And so we need to understand diffraction through round apertures to be able to describe quantitatively what the patterns look like that we gain from a microscope. So we find that diffraction through a circular aperture yields a Bessel function. That's also something we're going to be deriving in the next couple of instances. So, and finally, a message to take home. This won't mean so much to you at this point, but I think as we go through this, you find that if you want to generate an image of an object with light waves, then the contrast in the image, your ability to discriminate different parts of the sample in the image, that arises from phase differences in waves arriving at the image plane. So essentially the different phases from the waves coming from different points of the object, they will interfere constructively and destructively according to their phases, and it's that gives you contrast. So, you know, where they destructively interfere, you get dark patches in the image, and where they constructively interfere, you get bright patches. So phase differences and interference of that type are crucial to the formation of images. So I follow the notes in what I scribble, but I will just highlight the most important concepts for you as I go along. And so you can then refer to the notes when you look back through my lecture to go through details at your own pace. Okay, so first of all, the first thing that we will talk about is we go back to this problem of interference, and this arises from the fact that I've already mentioned that the wave equation is a linear equation, and so the principle of superposition applies. And so this means that if you have a field, let's say you have an electric field that is composed of several different fields. Let's just say call this one E1 plus E2 plus E3 and so on. Then if my individual fields are something like they have an amplitude E1 exponent I K1 dot R minus omega t plus phi 1, and the second wave has an amplitude E2 exponent K2 dot R minus omega t plus phi 2. Now, and so on for the different fields. Then the sum of those is also a solution to the wave equation. So that's what the principle of superposition is. So if individual fields are a solution, then the sum of these fields will also be a solution to the wave equation. And so there are several things to note. So what I've written is, so K1, you remember, is the wave vector. So we have K1 is equal to 2 pi over lambda 1 times 2 pi over lambda. So that means lambda is the wavelength again. So how often in space does the field amplitude vary, right? The smaller lambda is, the more quickly it varies. The larger lambda is, the more slowly it varies in space. And obviously at an instant in time, when you look at the point, it is important that you know what the phases are arriving from the different fields at that point. And so you get that by adding these phases correctly. And we have assumed in this case that all the frequencies, omega, of the light fields are the same for this example. And so omega is the same in all the fields here. Doesn't have to be, but for the discussion that we are going to have as we go forward for imaging, that will be the case. We also have included these phase offsets. And so we call, so this is the wave number. That's units per meter. How quickly it changes per meter in space. And phi 1 and phi 2 are phase offsets. So this allows for the fact that the starting phases of the light waves may be shifted in space. And now comes an important point. If the phase offsets theta 2 minus theta 1 are constant in time, then the waves are called, the waves are mutually coherent. The opposite case, so what that means is if you have two waves and they have a constant phase offset with one another, the phase offset will be maintained in time. And in contrast, if you have two mutually incoherent waves, then this phase offset is constantly fluctuating in time. And so you will not see interference in the same way with incoherent waves as you see with coherent waves. So we assume when we add up these phases that the phase relationship is maintained. So now comes the crux of this. We have said that what we measure in a camera, for example, or what your eye responds to, is not the field itself. It's not the field itself. It is in fact the intensity of the light. The field oscillations are so fast you cannot get the instantaneous amplitude. Nothing resolves it. It's cycling at 10 to the 15 times per second. So that's a million billion times per second. Nothing is fast enough to resolve this. So in fact, you are averaging over, whatever the response time is of your instruments. So for the eye, it will be tens of milliseconds or something like that. So really an enormously great number of cycles. And so the average intensity that you get, that you measure, is proportional to the square of the field, as we've mentioned in the last lecture. So the intensity is given by the square, which you can get by multiplying the field E with its complex conjugate. That gives you E squared, and that gives you the magnitude of the intensity. And so if I now try this by just, let's say, superimposing two fields, E1 and E2, let's suppose the total field has just two components in E1 and E2. So for E equals E1 plus E2, we get I is equal to E1 plus E2, and then we take the complex conjugate of that to give us the intensity if we square that. And so then we get terms E1 and E1 conjugate gives you this, E1 squared, amplitude squared of the first field plus amplitude squared of the second field. So you can see that, so if we take this field times its complex conjugate, then this part drops out because it gets to 1, right? So it's exponent I times exponent minus I. So this term becomes 1, and then you end up with E1 conjugate, which is the same as E1 squared, the magnitude of that. And that goes, and then we get these two cross terms. We get E1 E2 star and E2 E1 star, and that turns out to be E1 E2 times the cosine of phi. And so you can see why that might happen. So if I take E1 times E2 star, for example, so it's complex conjugate of this, so you get exponent I omega t and exponent I minus omega t. So the omega terms drop out, but these terms, so you will have terms k1 minus k2 dot r, and you have theta 1 minus theta 2 remaining. And so if the fields are the same, then what you get, let me just slow down a bit and go through this. But you see you get these cross terms in there, and you get them twice, right? And so what happens then is that 2E1 E2 cos theta is called the interference term. And this is quite interesting. So because what happens is you have theta here is equal to K1R minus K2R, because the minus because we're taking the complex conjugate, plus theta 1 minus theta 2. And so now you see that if the phase difference theta 1 minus theta 2 between the two waves is constant in time, then this will remain constant, this theta here. And so this term here will not be 0 unless unless the phases are such that the cosine lies at gives you 0 output value, right? But it will be a constant. It will be a constant. If, on the other hand, let's say you have an incoherent light source, so theta 1 and theta 2 are rapidly fluctuating in time, then that cos theta term will fluctuate rapidly in time. And then when you average, let's say in your eye or in your camera, over several cycles of the light, over many, many cycles, then they will fluctuate because that cos theta term will be negative and positive. It will take all values between -1 and 1. And so on average then, this term will drop out and you get no interference. So the interference you only get if these phase differences are maintained. So there are phase differences arrive because of initial offsets of the two waves, and also phase differences arrive because as they travel through space, the phase arriving at a point will depend on how often the amplitude is going up and down until it arrives at that space, so the distance traveled, right? So it's 2 pi over lambda times the distance traveled, r. Okay, so if we now take a simple case where, let's say that E1 equals E2 equals E, so they have the same amplitude, then what you can see is that the total amplitude from the two fields, E1 and E2, arriving at any point is given by 2 times I plus 2I cos theta. Now, just to go back, so E1 squared is the intensity of the first field. E2 squared is the intensity of the second field. They're both E, so that would be E squared plus E squared, which gives you I plus I is 2I. Then here E1, E2 is E squared, if they're the same fields, so that would be 2I. And then you have the cos theta term. So you see something incredibly interesting now. Depending on this interference term, the total intensity can vary between 0, because cos theta can be -1. So it could, so this term becomes minus 2I. So 2I minus 2I is 0. This is called destructive interference. And the other case is, the other extreme is that cos theta is equal to 1. Then you get 2I plus 2I is 4I, and the intensity reaches 4 times. This is really remarkable, right? So you're putting you're putting in I and I, but there are some points in space where you will get an intensity that corresponds to 4I, right? So it's a higher intensity than you might expect if interference wouldn't take place. On the other hand, there are also spaces where the phase differences are theta are such that the waves arrive completely out of phase, and the overall intensity then becomes 0. So the interference arises when we square the amplitudes, because then we get this cross term in there. And so in the image where we measure the intensity, we actually see we see the result of these of how the waves add up and interfere constructively. So with this formulation, we are already able to look at one incredibly important thing. One example of interference, which is the Young slit experiment. So let's consider the following experiment. If I take a plane wave, so the phase does not change across these planes of constant phase. So, and let us now put this through a double slit system like this. So you have one slit here and one slit here. We make them very small. So what happens now? After Huygens principle, we're now only admitting, so we get spherical waves emanating from all points inside this aperture. If the aperture is very small, we just get single spherical waves emanating. So here the wavelength is lambda, so this point here will be a point source emitting this spherical wave. This one will be a point source emitting this spherical wave. Let's just try to draw one more. It's hard to draw these things, of course. Something like that. And then what you see is if I go a distance like that, let's go in this direction here. If you put a screen a long place away from here, then what can you see? So light, the spherical waves arriving at that point. So if I take this point here, then the phase of light coming from here and the phase of the light coming from there will be exactly in phase, and the theta cross term will be 0, and so this 2e1e2 will be just 2e squared. This will be 2i, so we get 2i plus 2i, so the intensity here will be 4i, or yes, 4i for at this particular point. Now let's look at another point on this screen. If you look a long way, in what other direction might we get? So here we have constructive interference. So we call this an order, m equals naught. So a so-called diffraction order, because at this point here, the waves add up constructively. Now let's find another point. So if we look at a direction somewhere around here, so if I do this properly, so maybe if we go along this direction here, you can see these waves are adding up in phase. So perhaps at this point, this wave here, this spherical wave, takes a longer path than that one. But if that path is exactly one whole wavelength more than the other one, they'll end up being in phase again. And so you get another constructive point, interference point at that one. And similarly, of course, by symmetry, you get another order down there, m equals -1. So these are called the orders, diffraction orders. And so what we end up with here, if I plotted the intensity, it might look something like that. It might look something like this. So I need to come up here so you can see this. If I plot the intensity, you get a maximum here, minimum down there, another maximum here, minimum down there, maximum there. And if the intensity I, intensity will be 4i, which is equal to equals to 4e squared as it goes in so you have E coming in here and E going in from this point. So the intensity from this is I squared, E squared from that one. It goes from 4e squared to 0, right? And then up to 4e squared to 0 and so on. And you can see exactly how that works, right? Because the different angles, you will get different phase differences now. And that will lead to constructive and destructive interference. And you get this fringe pattern. And if you were to photograph this, so in the lecture notes you have a picture. This is the pattern you see on a long way away, and you can see exactly you get these fringes varying sinusoidally in intensity. So you have the zero order here, first order, second order, third order, and so 0 order, -1, -2, -3, and so on along this screen. Okay, and the important point is if these two sources here. Imagine, look at this point here now, and let's suppose we have an incoherent light source. Then, of course, this theta term here will vary very rapidly in time. And so the average of this cos theta term, if I average over several cycles, will average out to 0, right? Because essentially you can also think about this instantaneously, you may get a pattern. But if these two phases are different, then this pattern is doing this very rapidly, and it will average out so that what you get is actually just 2i averaged over the entire screen on the other side. So this, of course, is proof that light can be described in terms of a wave. You could not describe that using any other theory, which is something that annoyed Isaac Newton at the time, because he didn't believe in the wave theory of light. But this experiment is super important. So here's the man, Thomas Young. He was here in Cambridge as well for a good while. And actually, you see here a drawing that was it was original in his book, where he drew patterns of light waves exactly as we have from two slits A and B, and you can see wherever they constructively interfere. So there are patterns here where they are in phase at these angles, and that gives rise to the different orders. So you saw that, and of course, in between you have the negative orders, right? The destructive interference. Okay, so one important point is these fringes here in some ways. So we're now getting to we're sort of easing ourselves to the major intellectual concept of this. So you can tell, of course, that the fringe pattern that you see here, the fringe pattern that you will observe in Young slits, tells you something about these two slits. And here's a question for you. I want you to think about this problem, and I want you to imagine what happens if I make this width between the two slits here, if I make that larger or smaller, what happens to the fringe pattern here? Now, you will understand, of course, that the fringe pattern tells you something about these two slits. Okay, so in some ways it will tell you something about how far they are apart from one another. And so I want you to think about what happens to the pattern if you change the slit distance and why. And so the other point I wanted to make is that you actually have contrast here. So the intensity goes from 0 to from bright to dark, and so the image contrast, that just means brightness differences in the image arises from interference, and so we actually do need these interferences to take place if we want to have good contrast in an image. So you need to have light waves from the object arriving at the imaging device with sufficient phase differences, sufficiently large phase differences, so that you get changes in brightness.